All right, so in this video there are two somewhat different but related things. I mean, it's all related to spin, but I wanted to first talk about, just go over a little bit of doing the inner product, the inner inner product. Apparently I can't spell product, the inner product, which is the expectation value, expectation expectation value for the different eigen vectors, the kets that we've been talking about. And I also wanted to go through a little bit of a deriving the Pauli matrices. Pauli matrices. So I'll start with the first one. And so if you remember the inner product, or the expectation value, was of the form something like this. And if you remember, with this we have to do the complex conjugate for the bra. So this was the bra and this was the ket here. And so we can take our eigenvectors that we have for the different spin orientations. For instance, if we want to take, well, let's say for instance that we have prepared it in up, and we want to measure it, if it's right, if it's pointing right. And so this will be, so if you remember, right is the 1 over square root of 2, 1 over square root of 2. We don't really have to worry about complex conjugate because we don't have any complex numbers here. And then the up was the 1, 0. And so we also want to square this because we want the probability for this. And so this is going to equal, so it's 1 over square root of 2 times 1, which is 1 over square root of 2, and that will be squared, and then 1 over square root of 2 times 0, so plus 0. So this just equals 1/2, which is as we would expect. If we prepare it as up and then we measure to the right, we will find that it is spin right 1/2 of the time. We can also look at this, say if we prepare in, or if we prepare in up and we measure in up, what we will get is so we have 1, 0 and 1, 0, and so we can see, if we also square this, we can see that this 1 times 1, so 1 squared, plus 0 times 0, which is 0, which is 1. And so that's what we would expect. We would see 100%. 100% of them would be up if we prepared it as up. And we can sort of do it the other way, where if we prepare it as up and measure down, this will be 0, 1, and 1, 0. Squared. And so you see 0 times 1 plus 1 times 0 equals 0. And so we have 0 here. And so let's take a look at one of the somewhat more complicated ones, which contain the complex numbers. And so if we want, for instance, to do out, so I'll just say out since I can't really draw an arrow pointing out of the screen, but it was prepared in, let's say, right. And so for this, what we would have, so actually let's do in for this, just so we can kind of see more clearly the complex conjugation. So remember that in, if we were doing a column vector, was 1 over square root of 2, and I, that's an I over square root of 2. So for this, we actually want 1 over square root of 2 and minus I over square root of 2, because when we do the row vector, when we do the bra, then it has to be complex conjugated, and so that is the effect that we change the sign on the complex number here. And so we are multiplying by right, which is 1 over square root of 2 and 1 over square root of 2. And so for this we have, once again, we want to square this. So we have 1 over square root of 2 times 1 over square root of 2, that is 1 over 2, and that will be squared. Then we have minus I over square root of 2 times 1 over square root of 2, which is, so we have plus, and that will be minus I over 2, and that will also be squared. And so for this, 1/2 squared is 1/4, and for this, the I, so I times, I times I is equal to the square root of -1 times the square root of -1, which is just equal to -1. But then we also have this negative here, which makes it +1. And so by squaring this, we get 1 over 4 again, and 1/4 plus 1/4 is equal to 1/2. And so we can see once again that if we prepare it right, and then we measure in, that we will see in half the time. We would also see out half the time. So if we calculated this using out, so if we did just use the negative here and then positive here, we would also get out for half the time. So it's it's 50-50 that you get in or out. All right, and so now to change direction just a little bit. So we talked before about the Pauli matrices. So that was the sigma x, which was equal to 0, 1, 1, 0. The sigma y, which was equal to 0, -I, 0. And the sigma z, it says z, which is equal to 1, 0, 0, -1. And so if we want to sort of find these matrices, sort of, so let's say that we start with a matrix whose elements we don't know. So we'll call it A, B, C, D. And so we want to find the sigma z matrix, and so we will multiply it by this ket vector here, which will give us +1. That's our eigenvalue there. This is the pointing up vector, so we expect a +1. If I used the 0, 1, then we would expect a -1, but I am going to just use the +1, and that should be multiplied by our vector yet again. And so from this, what we can say is that, yeah, let's also do it with the -1, and so we will still need that in order to calculate this. So that will be the -1, and then 0, 1, so multiplied by 0, 1. And so from there, we can say for this one that we have A times 1, which is, we'll sort of explicitly put it there, A times 1 plus B times 0, and that will equal this top one here, so that should equal 1. And then we'll do the bottom here. So we have C times 1, so C times 1 plus D times 0 plus D times 0 equals 0. And so we know for this one that since this is going to be 0, because it's always 0, then A has to equal 1. And when something has to be equal, you'll often see it with an exclamation point over it, because because this is going to be 0, and so B could just be anything. But in this case, we have the A times 1, and if A was anything other than 1, then this would not equal 1. And for this, we have C times 1 plus D times 0, and it equals 0. That's what we got from right there. And so, once again, D in this case could sort of be equal to anything, but C has to be equal to 0 in order for this to be equal to 0. So we will write C with an exclamation point equals 0. And so I'll just start our matrix up here. So we know that A equals 1, and we know that C equals 0. And then we can sort of do the same thing here, where we have A times 0 plus B times 1. And so we have here, we have the A times 0 plus B times 1 equals 0, because it's going to be equal to this here. And for this one, we have C times 0 plus D times 1 equals negative 1. Because if we didn't have this eigenvalue here, it would be 0, negative 1. We've just taken this negative 1 out to make it into an eigenvalue. And so in this case, once again, we need B to equal 0 in order for this to equal 0. We already know that A equals 1, but that's multiplied by 0. And so we know that B is going to be equal, we know that it has to equal 0. And then for this, we have C times 0, and then D times 1 equals negative 1. So we know for that to be true that D must equal negative 1. And so B, we said, was 0. That's this up here. And D, we said, was negative 1. So negative 1 down there. And so this is our sigma z. And we can do kind of the same thing here for the other two Pauli matrices. I'm going to skip over the right-left one. I'll go to the in-out one, since that is the one that has the complex numbers, just so we can sort of see how that works with the complex numbers. So we have our A, B, C, D again, and we are multiplying this by our 1 over square root of 2 and our I over square root of 2, and so that will equal plus 1 times 1 over square root of 2 I over square root of 2. And we also want the other one here. So A, B, C, D multiplied by 1 over square root of 2 and minus I over square root of 2, and that should equal minus 1 times the 1 over square root of 2 minus I over square root of 2. All right, and so for this one, we can, and I'm going to label the the equations here. So we have our first, that will come in handy later, and we'll call this, we'll say that as A plus B I equals 1. And for the purposes of this, I'm going to ignore the square root of 2, since it's common to everything here. And so this would be 1 over square root of 2, but I'm just going to call it 1 to make it easier. And we will say that our second, so we see here that we have a times 1 over square root of 2 and b times I over square root of 2. Like I said, I'm just ignoring the square root of 2. These would all have square root of 2 under them, but just to make it easier, I'm going to ignore that. Then c plus di equals I. And so we can see this c times 1 over square root of 2, so we'll just say c times 1. Excuse me, and d times 1 is going to be equal to I over here. And then so for this one over here, we'll call it third, is going to be a minus bi equals, that's going to equal minus 1. So minus 1. And fourth is going to be c minus di equals, that's going to be equal to I. And so what we're going to do is we're going to add first plus third, and that will give us, because for this we are going to try and, because these both have a in them, we're going to try and find out what a is equal to. So a plus a is 2a, and then we have plus bi minus bi is 0, so I'll just sort of explicitly put that there. And 1 minus 1 is equal to 0. And so we know that 2a is equal to 0, so a must equal 0. And we can find out, so we know that bi has to equal 1 in this case, because we need the sort of a 1 minus 1 here, and so b has to equal negative I, because we are multiplying I times I, which is negative 1, and then putting a negative on it. So it's just flipping the sign. So we know that a is 0 and b equals negative I. So I'll put our matrix up here. So we know that a is 0, and we know that b is minus I. And then we can take second and fourth to find out c and d. So second plus fourth is going to equal, so we're going to have 2c plus 0 equals 2i. And so we know that 2c equals 2i, and from that we know that c equals I. And so we can put our I up here, and we know from this that that d is going to that d has to equal 0 here, or yeah, so c has to equal I. So d has to equal 0, because otherwise we're multiplying these i's together, and we won't get the 0 that we need. And so we know that d has to equal, that's an exclamation point there, has to equal 0. And so this was our sigma y Pauli matrix. And so that's sort of a way we can quote unquote derive these Pauli matrices, or at least we can do it as sort of just another way of seeing how these sort of pop out from what we are doing. And so yeah, I hope this was at least somewhat helpful for you, looking at at a few examples of the inner product here, and looking at the Pauli matrices in a little bit more in depth. Uh, yes, okay, and I will see you in the next video.